Okay, so I uploaded the lecture 3 this morning, and then I also uploaded an assignment, the first assignment in this course. Remember, assignments are worth about 25%, and the goal is to expose you to some of the software simulation tools to solve a variety of problems. And of course, I will demonstrate how to do that in class starting today. So this is due about a week from today. It's a fairly straightforward assignment for those that know MATLAB. So I need to poll again. How many of you have not used MATLAB before? Only one. Okay. So if you can see me, I can give you additional resources where you can watch. In fact, I have taught a whole course on MATLAB, and it's on YouTube, and you'll be able to listen to it. But you should be, are you comfortable with any programming language?
Done some basic, or I've used MATLAB programs that other people have created. I've just never coded anything myself.
Okay, that's fine. That's good enough, I think. How about concepts of programming languages?
Concepts, yeah. I mean, I've used nice specific programming language, but I've used software, statistics software that uses other type of language. So I'm familiar with setting up programs.
Right, okay, good. Let me know if you find the problem too challenging, okay, and then we'll address it. But MATLAB is a relatively easy environment because it's a very forgiving environment and that's interactive. I will show you how to do some debugging that might help in writing and testing programs, stuff like that. So you can download that assignment from there, and once you are done, you need to have it as a single file. You can capture it from MATLAB as a report and then upload it to Moodle as well. Don't send it by email. Pardon me?
You need the M file?
Well, you can list the M file into the same Word document. Okay, so yeah, so you can capture everything that MATLAB produces as a report in a Word document, and if you want, you can cut and paste the M files that you use to generate the report. And in one of the lectures, maybe I will show you how to generate a report as well, or maybe even today if there is time. Okay, and please feel free to stop and ask specific questions that you have as you're doing assignments, certain features that you want to know about. The best way to learn, of course, is to open up the help manual as you're going along, because there are context-sensitive helps. And the manual themselves, if you want to read and learn a language, that's not the right way to do, because these are 800 pages long manuals, right? So learn as you need. And these languages are, the environment is structured in such a way that you can do that. So I will show you how to go about doing that. Okay, so, and after the lecture, of course, I put the links to the videos. But let me just open up today's lecture. I have only about 6 slides or so today. I'm not going to rush through 40 slides like we did in the last 2 lectures. But in the last 2 lectures, my goal was to kind of give you an overview of what are the motivations, what are the driving forces for us to understand and learn these topics of advanced simulation in related to transport phenomena. That is fluid mechanics, heat transfer, mass transfer, reaction engineering, thermodynamics, etc. How do we set up the models that are high fidelity, and how do you get solutions to those models? And what are the motivations for that? And so we specifically in the last lecture looked at specific examples of oil spill, bubble columns, fluidized bed reactors, packed columns, stirred vessels, etc. So there are about 400 different unit operations that are commonly used in putting a chemical plant together that takes some raw materials and produces a finished product. And this is also true in food processing, it is true in mineral processing, it is true in, of course, oil and gas. In power plants, we take, for example, natural gas or coal and combust it. There is reactions involved in there, and then we produce either steam and drive a turbine. So there are lots of multi-phase flow fluid mechanics problems along the way in a very broad range of industries, automotives, aerodynamics, every place. Okay, and we also saw that in many of these places there's a spontaneous transition from a homogeneous to heterogeneous regime, and we understood that as being caused by small dense. When you have what do we mean by multi-phase flow? Two different phases, two different materials. So obviously they have two different densities, and if they have two different densities and they are in a gravitational field, they experience a differential force. That is what we call the buoyancy versus weight, right? And so even if there is a very slight variation in the concentration of the distribution of these particles, it will set up a convection current. So homogeneous condition is very difficult to maintain, in fact, in most of this equipment. The conditions are heterogeneous. And so we saw how we traditionally design using empirical correlations for friction factor, for Nusselt number, for Sherwood number, etc. But they don't scale up very well because they're often measured in a small scale equipment where only small structures are possible. As you scale it up, when you have large scale structures, large flow patterns are possible that are not embedded into those correlations that are measured in small scale. And so we need to develop a framework that will capture the large scale motions for us, and that is computational transport phenomena. It does that for us. And also we saw that advances in simulation coupled with advances in manufacturing of complex shapes like the fractal shapes that we saw, and advances in advanced measurement technologies provides us a unique opportunity for design innovations in process equipment design. And that's what our group, research group at LSU is about. We call ourselves EPIC, Enabling Process Innovation Through Computation. And this course is about one aspect of that, computational transport phenomena. We're not going to talk about, the whole course can be given on advanced measurements, tomography-based measurements, laser Doppler anemometer, hot wire anemometer, etc. And we are not going to talk about advanced manufacturing. In fact, mechanical engineering, there are courses there where you are looking at lithography, 3D printing, computer-aided milling, machining, etc., to produce complex-shaped vessels, complex-shaped stirrers, inserts, etc. Once you can dream, using CAD, you can develop that geometry and send it out to the manufacturer and get the parts assembled and brought back to you. So the modular manufacturing then is emerging as an opportunity for producing small-scale modular plants, but repeat them many units so that you can achieve the scale, large-scale production. But at the same time, you don't introduce large-scale motions inside such vessels, and so you have control over the design. Okay, so you don't need a 20-year development time to develop a slurry bubble column reactor, for example. Okay, and so we saw the challenges in food-water energy nexus, so-called the interlinks, connections between food, water, and energy, as a challenge where the rates are not in balance. The rate at which we consume hydrocarbons and convert them into CO2, whether it is for food, whether it's for transportation, etc., is much higher than the rate at which nature can refix the carbon dioxide into hydrocarbons with sun's energy. So ultimately, everything that happens on this planet, you can think of it as substantially being run by nuclear energy coming from the sun. We can complement it by nuclear plants on Earth. And of course, the other source is the geothermal energy as an extra energy. But all other forms of energy are essentially nuclear energy stored at some time or other. Fossil fuel, hydrocarbons, coal, etc. Wind energy, we talk about wind energy, but that is also essentially captured by sun's energy that creates this atmospheric motion, which we harness in the form of a windmill. Wave energy, where the surface waves are used to extract energy from that. All these ultimately come from sun's energy landing on the Earth. And there was a talk that I listened to where I was really startled to hear that. Maybe I'll post this as a question. Okay, if you have to harvest sun's energy to supply humanity's current energy needs, how many square miles of land do you think you will need? Suppose you have photovoltaics. Okay, you can lay the photovoltaics in as large a land as you want. Has anybody come up with that number?
The size of a country in Africa, that's what we said. I can't remember which country it is. It's about the size of a country in Africa.
That may actually be big unless it's a very tiny country. The number that I have heard from a very credible source is 100 square miles. Okay, 100 mile by 100 mile. You take that. If you have a land like that, and in California in the desert you have that, right? If you can cover that with solar energy, and that is the total energy that is absorbed in that land. If you can all capture it, you cannot, of course. Photovoltaic efficiency is 7-8% or so. There are technological improvements, and it can apparently go to 20% or so, according to Elon Musk, I think, in recent times. And so the sun gives us plenty of energy. Okay, just how we balance, how we manage that, I think, is important. We are consuming it at a very rapid rate of all the energies that were stored from the past. That's the reason for CO2 increase. And tomorrow's seminar is going to be about the CO2 capture, sequestration, etc., I think. So that's to just give you a general overview of what are the motivations for using advanced simulations to innovate process designs. Now you're going to get to the nuts and bolts of how do we develop these models. Going progressively over a series of 6 to 8 lectures, the most sophisticated models that we can assemble that are coded into COMSOL, into Fluent, etc. At that time, you'll be able to open up a project. Until then, we'll keep you busy with assignments like this. So this is a very simple example from undergraduate heat and mass balance, mass and energy balance course. What is happening here is you have a simple recycle stream. Okay, so you have, I guess I should. Let me just enable the pointer. Okay. I cannot blow it up now. Can you read that in the back? Not quite. I don't know if I enable this, it's not allowing me to zoom. Oh, okay. All right. Okay, I think you can see the hand there, right? Can you? All right, so we will use that as the pointer. Okay, so you have a reactor into which you are feeding carbon monoxide and hydrogen, and your goal is to produce methanol. Okay, so partial conversion takes place in the reactor, and then you take it to a condenser and you condense the methanol out, and the gaseous carbon monoxide and hydrogen are recycled back into the reactor. Okay, so our goal is to find X, Y, R, and P. Okay, R is the recycle rate, P is the product rate, and X and Y are the mole fractions of carbon monoxide in the inlet stream. Okay, so it's a classical undergraduate heat and mass balance equation in this particular case. So you are given all the other information about what is the flow rate in between the reactor and the condenser. So the problem could, in 2171, what you get trained is in how do you formulate the problem once I switch the specification. So in this particular case, I've given you all the compositions in the intermediate stream, I've given you the compositions in the recycled stream, but I want you to find the inlet compositions. Typically, you will find the inlet compositions are given. I need to find the outlet rate and the compositions somewhere in the in-between or in the recycle. So your job is then to identify how many equations can you write, how many variables are there, what is the degree of freedom, that is the difference between number of variables and the number of equations. We are not going to worry about any of those. Okay, we are focused on computational aspect of it. I'm using this as an example to show one class of problem which is almost trivial, that is a set of linear algebraic equations. Okay, so what you see here on the right side are the equations. Okay, so for the inner loop you write a carbon balance. The carbon balance simply says how many atoms of carbon are coming in. So every mole of CO carries one carbon. Okay, so there are X moles that is coming in, so X plus this stream is the stream that is coming as a recycle. Okay, so that is coming as recycle, that's why it is added. This plus this must equal what leaves the stream. So that is my loop, the inner loop over which I'm making a material balance, looking at carbon count. How many moles of carbon are coming in? How many moles of carbons are leaving? So there is one stream that comes through this, one stream that comes through the recycle stream. But I know for the recycle stream, there is 0.302 coming with CO, and then there is 0.004 coming with the methanol. Methanol is also not completely separated, so there is some of it that is recycled. So you will see that it is 0.302 plus 0.004 times R. These are the mole fractions multiplied by the molar flow rate R. And that should equal what leaves that inner loop. Okay, and that is this part. That is F times the carbon that is leaving through this, which is 0.274 plus 0.095. Okay, so you say 0.274 plus 0.095. Using that concept, you write an equation for hydrogen, you write an equation for oxygen, and continue to assemble the equations. Things like Aspen does this automatically for you. The process of assembling the equation has been automated. So in Aspen, all you need to do is take these icons for a reactor or for a separator, connect them, and identify what are the various flow rates and compositions for the inlet and the outlet. It assembles the equations for you. Okay? Because this assembly of equations can become very tedious if you have thousands and 10,000s of equations. These days you can have literally billions of equations, and that's why we need computation to solve. This problem doesn't need computation to solve, but we are going to see how MATLAB will solve it, how COMSOL will solve it, so that using a simple problem we learn how to use COMSOL or how to use MATLAB to solve a problem like this. So any questions on that? How these equations come from? Because I'm going to leave that at that, and I'm going to kind of ask you to make sure that you understand how the other equations are written. Okay, so the first equation, inner loop carbon balance, after you simplify it, after you add this, the equation becomes like this: x plus 0.306R equals 101.475. You do the hydrogen balance like that and simplify that as y plus 0.702R equals 225.75 over the same inner loop. And you do this for the oxygen balance. Okay, and you get x plus 0.306R equals 101.475. Do you notice anything funny in the three equations that we have written? First and third are the same. Okay, why is that happening?
Because C and O are present together
Everywhere. So the stoichiometry in the reaction and the structure of the reaction dictates that these two equations are dependent on each other. Now, in this case, it was obvious. You can just see because the coefficients are the same. But the concept of linear dependence you would have seen in linear algebra. As I said, to understand this course, you need to understand linear algebra and a bit of differential equations. And then we are going to use computations to reinforce those ideas and to learn how to solve these equations. Okay? So we would call these three equations are linearly dependent on each other. The first depends on the third. In fact, it's the same. But you might have a situation where they don't look the same. They don't have the same coefficients. But through a suitable combination of second and third, that is, I take the second equation multiplied by a number, every term by a number, which I can do because I don't change the equation, and I take the third equation multiplied by a different number and add them up, and if I get the first equation, that means the first equation is linearly dependent on a linear combination of second and third. Okay? So if that happens, we are in trouble because we don't have three equations, we have only two equations effectively, right? How do you test that in linear algebra? Do you remember that? How do you test for linear independence? Put this in a form of a matrix and calculate the rank of a matrix, right? So there is a function in MATLAB called rank. So once you assemble the matrix, you just say calculate the rank, and it will tell you what the rank is. So if you have a 3 by 3 matrix and it says the rank is 2, it means that only 2 of them are linearly independent. The third one is not. Okay. Then I take the outer loop. Okay. I take the outer loop that you see here and I assemble two more equations. Okay. X equals p and y equals 2p. And that's fairly easy to see also. Because you have x, there's one carbon atom that is coming in, and is it carbon? Yeah, x is equal to p because one carbon comes out. Okay, but for y, which is hydrogen, 1 mole of hydrogen comes in, but 2 moles of hydrogen leave. Okay, so y is equal to 2p. x is equal to p, y equal to 2p. So now we have 5 equations, but only 4 are linearly independent, and there are 4 variables. Okay, you can assemble them in a vector matrix form, and that is part of the exercise in any problem. In preparing it for solution by a computer, once we have formulated the problem, you should be able to enter that into MATLAB or COMSOL, and we will see both. Okay. Any questions on that? It's a fairly simple problem, right? And you have to find the solution for x, y, or p. Are they coupled? What do we mean by when a system of equations is coupled? That's an important concept, right? You need to know that if I make a small change in x, is it going to change every variable, y, r, and p? Okay, so you might say, but if I look at the fourth equation that has only x and p, so if I change x, is it going to only affect p? The answer is no, because if I change x, it will affect p, but p will affect y, but y will affect r, etc. Right? So under what conditions you will see that a matrix is, or a system is uncoupled? If you have an identity matrix, it is, you hit it on right on. It is completely uncoupled. What does the identity matrix say? It's essentially 1 on the diagonal, and you have a vector x, y, r, p. So whatever is x is equal to the right hand side, y is equal to the right hand side, etc. Okay, that's very good. So I think does everybody else see that? Okay, so by coupled we mean that all variables depend on every other variable. Okay, so I'm going to give you a case where the matrix is, after I have assembled, is not identity matrix, but it is a lower triangular matrix, meaning all the elements on the diagonal and the elements below the diagonal are non-zero, but every element above the diagonal is 0. Is that coupled? In what way? It's one-way coupled. Why? Because if you take the first equation, all these are 0, I said, because it is lower triangular, right? So I multiply by x, and then I will set that equal to the right-hand side. So the first equation only depends on x. The second equation has 2 numbers that are non-zero, right? Everything below the diagonal is non-zero. Everything above the diagonal is 0. Okay? So when I take the second equation, if I had a non-zero term here, right? So that times x plus this times y will be equal to the second equation. But I already know what x is from the first equation, right? So I can solve for y. So you can sequentially solve. So it is a one-way coupling in the sense x is independent, y depends on x, z depends on both x and y, etc. Okay? Do you understand what I'm saying? Now I'm going to give you a different situation where it is upper triangular matrix. Is that coupled or not? Again it's coupled. Which way is it coupled? From the last, one way, right? So what you would do is you would simply change the direction and say I'm going to solve for the last variable initially, and then go to the next one. There will be 2 unknowns. I will solve for 1 because the other one is known from before. Do you see where this is leading to from your linear algebra? What do you do in Gaussian elimination? What do you do in LU decomposition? These are all exactly the same thing. So if you're given a matrix like this, you can decompose that into a lower triangular product of a lower triangular matrix and an upper triangular matrix. MATLAB has a routine called LU. Okay? And the first assignment is about review of these concepts. Okay? So construct a matrix, a tridiagonal matrix, and then play with LU decomposition, determinant, eigenvectors, eigenvalues, everything that you have seen in linear algebra. Just recall that kind of a thing. Okay? Any questions? So the way of solving this, in the next 2 or 3 lectures, what I'm going to do is formulate these problems as examples, the simplest example possible, and show you what tools are available in MATLAB and what tools are available in COMSOL to solve such problems. So we will take linear algebraic equation, non-linear algebraic equation, and differential equations, initial value problems and boundary value problems, linear and non-linear. But if you are doing it numerically in a computer, it really doesn't matter whether it's linear or nonlinear, except maybe for algebraic equations. We'll see the advantages and disadvantages of that. Now, in going from equation 1.7 to 1.8, I have done something. What have I done? I have eliminated one variable because it was simple to do in this particular case. I don't have to do it. I can let computer do the Gaussian elimination. That's exactly what computer does. Eliminates one variable at a time from every equation to convert a full matrix into a lower triangular matrix and an upper triangular matrix. So in the forward elimination process, you end up with a lower triangular matrix. And the reverse one, you'll solve the upper triangular matrix. But here I was able to eliminate P, so I formulated as 3 equations and 3 unknowns by simply substituting wherever I had P in terms of R. Because one of the equations that I had was simply, if you compare x equal to P and y equal to 2P. So wherever I had x and y, I could replace that, okay? Or P in terms of x and y. So that's the simplest problem, simplest example that we have. Okay, and should we go and build some more problems or switch to MATLAB and COMSOL to show how we would solve that? Maybe we'll switch to MATLAB and COMSOL and see how we solve this problem and come back and take the next problem and solve it in both of them. Okay, so let's do it in MATLAB. So if you go to the next room, that's a computer room, you'll find all the computers there have both MATLAB and COMSOL. Okay, so I hope I can check out the license here. There is a student edition of MATLAB. If you want to buy it, it's a good investment for $100 or so. COMSOL is more expensive, but we have a classroom kit that's installed on the machine next door. So this is what you see in MATLAB for the benefit of those that have not used MATLAB in recent time. It's a GUI based, graphical user interface based, and there are many windows that you see. And one of the most important windows is the so-called command window, through which you interact. You enter a command, it immediately interprets it and acts on it, executes it, and produces the result as a printed output, if there is any result to be produced. Okay? But you also have a number of secondary windows that you can customize. So here you have something called a workspace. Right now it's blank, but when you create a variable, those variables will be listed in the workspace. And here you have the editor window where you can edit functions, and we will see some examples of those as well. And here you see the current folder and the files that are in the folder. And here is how you set up the path. So I'll just pick up the path for our lecture. And you will see there are a number of files that I have created. But before I create this, let me just show you how I would do it. I just wanted to see the function from here. So the interactive commands are very simple. For example, if I say that you see in the notepad window, A equals 10.306 semicolon 010.702 semicolon minus 210. This is a 3x3 system that I showed you. All you have to do is just type it as you see. Let me just copy and paste that. But you can type it with a keyboard. Okay, I'm just accelerating my typing job. So that's what it is. So you type a set of numbers between square brackets, separated by space, if they're all in the same row, and separated by a semicolon to start with euro. Okay? So this is going to create a 3x3 matrix that we just developed. Okay? And once you hit enter, it defines that variable and echoes that and shows you in a pretty 3x3 format. But you also see in the workspace a new variable A has been created. Okay? Similarly, I want to create the right-hand side, and here I copy and paste that. So B is equal to square brackets once again, another 1.475, but semicolon, because to show that it is a second column. and then the second number, semicolon, and the third number, etc. If you didn't put a semicolon, if you had a space, it will create a row vector. But that's fine. You can transpose the row vector into a column vector very easily. So it's going to create another variable called b. Okay, but b is going to be a column vector, as you see here. Okay, and getting a solution to this in MATLAB is extremely simple. All you're going to do is x is equal to a backslash b. The backslash operator is the Gaussian elimination algorithm. So we are going to see later on the first third, after finish the first third of the course in model building and how to solve. So as I build the model, I'm going to show you how to solve in these two environments so that I can keep you busy with assignments as you're learning into the theory of model building and then the algorithms. The question of how this backslash operator solves this particular set of 3x3 equations, we will see as a Gaussian elimination, LU decomposition, etc. But that is your x, a vector x. Okay, but we need to know what does that vector mean. We will know that by comparing how we packed it. So the first one is lowercase x, which is the molar rate of carbon monoxide. The second one is y, which is molar rate of hydrogen, and the third one is r, the recycle rate. Okay, so you pack the variables in a particular order, and that order is determined by how you enter these equations. You can switch these equations, but that doesn't matter. Okay, but if you switch the columns, what do you have to do? You have to change the order of the x, y, z variable. Okay, but if you change the rows, it doesn't really matter. Okay, if the solution will remain the same, the vector will be packed in the same order. Okay, any questions? Am I going at the right pace? Slow, fast? Okay. At this stage, you can begin to play with MATLAB commands. For example, what is the determinant of A? There's a function called DET. Okay, so it tells you what this is. There's a function called EIG. So you can say what is the eigenvalues, the three eigenvalues of A. Okay, so these are the three eigenvalues. But of course, you must know what an eigenvalue is, what a determinant is. Okay, so there is something called LU. That function does the LU decomposition of A. Okay, and the answer, of course, it has to return two matrices, the lower triangular and upper triangular matrix. If you don't provide a placeholder for how it returns it returns only one of them. But if you had entered the same command with L comma U, okay, on the left hand side, if you say L comma U within square brackets and then say equal to anyway, I'm not able to see that. Let me see whether I can blow up the. There is a way to. There is a way to increase the font size, but they keep changing these layouts, and every time I teach, I need to find out where they are. Not a new script. Add-ons, preferences there. I don't mind doing these, searching for it in the class, because you should feel comfortable doing the same thing. Don't expect instant answers. Spend some time looking for it, and you'll find that it's not very difficult. There it is. Preferences, fonts, and this is 10, so I increase it to 18. Apply. Now it's better, right? And so if I do this, then I expect to return, MATLAB to return two matrices, L and U. Okay? And you find that U is strictly upper triangular, right? But L doesn't appear to be. Why is that? L is lower triangular, but the way that it assembles this, does the LU decomposition, during that time, it will switch rows and columns to make sure that there is something called diagonal dominance, I guess. So as it solves these equations, it's called pivoting in the Gaussian elimination language. So when it switches two rows, remember it means that you are keeping track of changes in the variables. So there is something called a permutation matrix that it keeps track of. Okay? So all these might puzzle you. Then the question is, of course, you should have a strong grasp of linear algebra. Okay? And you can say help LU. Okay? and it gives you a lot of help on what LU function does. Okay, so it actually returns more than L and U. It returns something called P, and P is the so-called permutation matrix that it generates as it solves a problem to switch to rows because it found a 0 on the diagonal. And when you have a 0 on the diagonal, you cannot divide by 0. So it has to switch it with some other row to continue the process. Okay, and so if you multiply P by what is that? Say that again.
So the equation for Ly equals PB, so
Right. Yeah. Exactly. Yeah. And there are a number of other factorization schemes you would have seen also in linear algebra: Cholesky factorization, QR factorization, incomplete LU factorization, etc. All these methods there is a function to implement those rules. So functions in MATLAB are nothing but a rule. So it takes certain input. In this case, it took the matrix A, and the rule is using algorithms or rules from linear algebra produce two matrices, L and U, which when I multiply together should give me back A. Okay, so you can write your own rules, you can write your own functions, and that's an important part of our ability to solve problems because only we know what the problem is. MATLAB doesn't know what specific problems we are solving. It knows if you give me an algebraic linear or nonlinear algebraic equation, MATLAB knows how to solve it, but it doesn't know what equations that we need to solve. So we need to program that. So we can write our own functions. Just like LU is a function that is built in, we can write our own functions, and we will see that as an example today when we move on to the nonlinear problem. Okay. So any questions about MATLAB, about linear equations? I mean, this is a 5-minute introduction to linear algebra, but I'm assuming, as I said, that you know linear algebra, how to formulate linear problems, and if you have linear problems, how to solve them. Okay, there are a number of other algorithms also for solving linear systems that we will see later on. Any questions? If there are no questions, we'll move on to how I would do that in COMSOL. It's a bit cumbersome. MATLAB is very elegant for these kinds of problems, but COMSOL is very elegant for solving partial differential equations. For solving algebraic, linear or nonlinear, and ordinary differential equations, initial value problem or boundary value problem, MATLAB is very good, very convenient. When you go to PDEs, MATLAB gets very complicated to use. But COMSOL traverses that trajectory very well. But you cannot write one line like A equals in COMSOL. You need to enter the whole function. So let's just start how that would look like. So again, go to the next room and you will look for a COMSOL multiphysics. Here you will find that there are a number of tools that are available. But what you need to pick is COMSOL Classroom Kit multiphysics. Click on that and it checks the license from the College of Engineering server, starts an instant of COMSOL simulator for you. It's entirely GUI driven. MATLAB has a GUI, but it's still a scripting language because you need to type the script, you need to type a command, and it interprets the command. You can put a series of commands into a file, then you call that as a script. If you enclose it with a function, then it is called a function with a definite input and an output. But script is any MATLAB command that you can put into a file and execute that. And in COMSOL, there is a link to MATLAB, so you can actually write MATLAB functions and feed them into COMSOL. But for that, you need to start in a slightly more complicated fashion called the server-client fashion. So you will start a MATLAB server, and it will talk to COMSOL. Okay? But this is the simplest COMSOL starting. So just pick the multiphysics icon and click on that. And it's very beautifully written. So you can start with a model building as a wizard or a blank model. Okay? Let's just start as a wizard. Wizard essentially helps you build a model. In a blank one, you need to know how to build a model. So from a second time, third time on, you just short the wizard and then go directly into building the model. But for the first time, I'm going to pick the wizard. Once I pick the wizard, it tells me, I don't know how to blow this up, it tells me that I can solve a 3D problem, a 2D axisymmetric problem, a 2D problem, a 1D axisymmetric problem, a 1D problem, and a 0D problem. Okay, so we need to know, we need to develop in this course, what do these mean? Where do these models come from? Okay, so the D here, the space dimension, as it says, select the space dimension. Okay, stands for in how many spatial dimensions a particular dependent variable changes. Okay, if I have a 3D problem, it means it changes in all the 3 dimensions. Okay, that's a partial differential equation for you. It can be a heat transfer problem, it can be a fluid mechanics problem, a mass transfer problem, a reaction engineering problem, an electromechanics problem, a solid mechanics problem. Okay, that is why it is called a multi-physics. It has all these models built in, and you can select these models, and we will see how that is done. Now, 2D axisymmetric. There is an icon, I don't know whether you can see it at the back, which essentially shows you some sort of a donut-shaped, a torus, right? So what does axisymmetry mean? It is a symmetry about an axis. So if you have a vertical line, and if you take an object and then rotate around it, and it remains the same everywhere, then like a donut. You cut a donut everywhere, you just see a circle, right? So if it remains the same, that you call that as an axisymmetric model. And there are reasons why we will come across axisymmetric models when we look at the fluid mechanics models. And then you have 2D. 2D axisymmetric means any plane, variations are there in 2 dimensions, but in the 3rd rotational dimension, there is no change. So the problem effectively is a 2-dimensional problem. And you can have a 2-dimensional planar problem. What did I do? Did I click something? Yeah. A 2-dimensional planar problem simply says, I have variation in an xy plane, but if I push through in the 3rd dimension, not rotate, but push through in the 3rd dimension, I have the same variation. Okay? And that would be a 2D planar symmetry problem. And you have similarly 1D, one-dimensional axisymmetric, and one-dimensional planar, which means things are varying along one line, or one line in an axisymmetric fashion. Okay? And then 0D means there is no spatial variation. And that is what is going to lead to algebraic equations or ordinary differential equations. Algebraic, if the what is going to determine that, whether it's an algebraic or an ODE, whether there is a variation in time, because this is talking only about space, right? You still have time as an independent variable, so things could change with time, and that is determined by whether it is dynamic or whether it is stationary. That's a choice that we need to make later on in ComSol. At this stage, it's just spatial dimensions, and 0 dimension means that there is no spatial variation. So our model is essentially a lumped model. If you look at inside the reactor, you may find that the composition of methanol is not the same everywhere, right? And if that is the case, and if you want to model that, you need to use a CFD model inside a reactor. But the reactor now is a black box. We are putting in something. We get an average concentration of methanol that comes out. Okay, so it is, we have ignored what happens inside, assuming that it will be the same everywhere. Okay, so let's select 0D. Any questions on that concept of spatial variations? Okay, so next it says, okay, you have told me about the domain where things are changing. It's 0 dimension. What kind of physics do you want to solve? Okay, and here you will find that there is chemical species transport, electrochemistry, mathematics, AC, DC, but we want to solve a global ODE or DAE. What does ODE mean? Ordinary differential equations. DAE stands for differential algebraic equations. So it's a mixture of a dynamic differential equation, some algebraic equations. So it has algorithms to solve both classes of methods. In MATLAB, we didn't see that, right? But there are tools that are available that we will see later on. So you have selected space dimension here. So if you want to go back and change it, you can do that. But we have selected the space dimension. So let's select global ODE and add that. Okay, so it adds that. And you can then go to study. So it is guiding you. The wizard is guiding you towards how to assemble your problem. Okay, and the way that it is assembled is becoming very common in number of simulation environments. Star CCM, Fluent, they're all kind of copying this idea of building a briefcase with your problem definition consisting of folders. Each folders will have some information about the physics, about the mesh, about the geometry, about the boundary condition, about the results, etc. Okay, so in this case, we have done that. So you can say go to study, the next arrow for pointing forward. and it says, okay, what kind of study do you want to do? Is it a steady state? Is it a dynamic? Is it an eigenvalue problem? You want to solve it in frequency domain, etc. We are going to pick stationary because ours is an algebraic set of equation. So you select that and then you say done. Okay. So the wizard has built in the first column the model builder. This is where you will see an overview of what folders you have built. Okay. So there is an untitled problem. You can title it anything that you want. And global definitions of materials. This is where you will have properties: heat capacity, viscosity, thermal conductivity, diffusivity, etc. There is a database from which you can pull if you know the material, or you can enter the values yourself arbitrarily. Okay. And then component 1 and definitions. And here you can define any symbol and assign it a value. That variable, when it is needed in any simulation environment, will be taken. It's like a global variable pigeonhole where you put some numbers, and then whenever you need, like CP, like inlet temperature, inlet flow rate, any parameter in the problem, you can define it here. So then you go to the global equations. This is where you actually define. I'm sorry again, I don't know how to blow this up. Okay. This is where you define your equations, the variables and the equations. Okay. These are algebraic. It actually can be an ordinary differential equation. You will see that u by default is a symbol for the unknown variable, and ut here stands for the time derivative of first derivative of u. Utt stands for the second derivative of u, and t itself appears there. So that function can be a function of time as well. So if you define such a function, and if you invoked time-dependent problem, it's an ordinary differential equation. It will integrate that. You need to provide an initial condition, and you'll provide the trajectory of that u as a function of time. Okay? So you can handle up to a second order ordinary differential equation. But if you didn't have ut or utt, you don't have to have it, right? If you didn't have it, what do you have? Just an algebraic equation. Okay? So you can define the algebraic equation in these rows. So if you have many equations, it will automatically expand the rows, and you can enter as many as you want. But the way that you have to enter is, you have to, you see the template. This is why I like console, because it gives you a feedback all the time. So how is the equation written? The equation is written as f is equal to 0. Okay? So if I go back to that particular equation that I had in the notepad, okay, oh, I guess not in the notepad, in the, yeah, in here. So I had, for example, x plus 0.306 equals 1. But if I want to enter this into that row, the way I need to write that is x plus 0.306r minus 1 over 0.475 equal to 0. Okay. Once you understand that, you can enter as many equations into those rows and then solve them. Okay. So I need to switch back and forth here. So I have x, y, and r. Let me take this form of the equation. Okay? So x, y, and r, and I'm going to input those things. Okay? So you need to be patient with me. What do I have? X plus 0.306r. X plus 0.306 times r minus 225.775. Okay. Now it gives me unknown variable because I haven't declared what are the variables. When I enter, you can think about it. When I enter an equation, I can introduce a lot of symbols. I have to tell console which is the symbol that I'm solving for. You can obviously have more than one symbol. So I need to identify in each equation at least one symbol that corresponds to that so that it knows, it labels them as the unknown. So here I can say x is my unknown. Okay? But still it's going to give you the warning. Whenever it gives you in a color other than black, it's simply says that the equation is not completely defined because there are symbols there I don't know. Now, if you had this symbol as a parameter, as a constant, you can define them in the definitions. It will take the value from the definitions and use it there. Okay? But here R is a true unknown, so I want to leave it as an unknown. Okay? So then I go into the next row. It automatically gave me the next row. Here I will put Y, and then I will put the equation for the second one, which is Y plus 0.702R. Y plus 0.702R minus.
That's what I find.
Pardon me?
This one is 225, and the first one should be 100.
Did I make a
101.47.
mistake? Okay, what?
This is 225.
This is 225. Okay, 225.725. And what was the first one? 7? 775. Okay. And what was the first one?
Half of that.
101.475. Okay. I have.
1.475.
I'm sorry. My memory is too. 101.475. 101. Okay. So, and the third one is minus 2x plus r, right? Minus 2x plus y equal to 0. Minus 2x, thank you. Didn't complain.
So like in the third equation we don't have r, so keeping it as a variable.
That's because it's coupled, right? So each equation has only two variables in this case, right? But they're all coupled, right? So you don't have, if you're asking, do you need to put a 0 times r, in MATLAB you need to do that. But in COMSOL, because we're just defining each equation, we just define it as the way that it appears. You don't have to put the non-zero, the 0 terms. I hope it's going to work because it still stays unknown variable r.
What if we keep x on the third row and r on the
You mean switch? That's a good question, right? Did you understand what his suggestion is? How do we associate any one of these variables with any one of these equations? There is no need to do that. In MATLAB, you don't do that. You just create them as a vector. You create a matrix, and you solve that using Gaussian elimination. So there's really no need to associate a particular variable with a particular equation. But COMSOL's expectation is that you will associate. So the next question is, what would happen if I flip them around? It shouldn't change anything because it should still solve the set of three equations in the three variables. Any other questions?
What kind of cases does it what kind of cases does it matter?
For linear system, it shouldn't matter. For non-linear systems, it might matter in the convergence. Okay, and we will have to see how nonlinear equations are solved so that you understand what we mean by convergence. Because in a nonlinear system, it's a trial and error process. In the linear system, there are two classes of methods: the so-called direct methods, LU decomposition, Gaussian elimination. There is no trial and error. We just systematically follow an algorithm and we get the answer at the end of a finite number of operations. Whereas there is also a method called an iterative method. Conjugate gradient is an iterative method. Your first assignment I'm asking you to use it too. There is a function called CGS of that. So there you need to provide a guess for x, y, and r. And then it will take that, plug it into the equation, and see whether the residual is 0. If not, it will try to come up with a better guess and iterate the process until it tries the residual. So each one is a residual, because what do we want? We want all this to be equal to 0. We have not explicitly said that it is equal to 0 because it is asking only for the function. The right hand side is equal to 0. So it's going to drive the function to 0. COMSOL's job is to take these variables and guess different values and drive them to 0. So if you take that approach, it doesn't matter whether it's a linear or non-linear problem. You can always guess and check whether the residual is 0 and drive it to 0 by updating the guesses. And in fact, there is a whole class of methods called method of weighted residuals that are based on that idea of making a guess for a variable or a function, testing the residual, and developing a scheme to drive the residual to 0. That's exactly what COMSOL is doing here. It's not solving a linear set of equations here. It's a nonlinear set of equations, I think. Okay, any other questions on this? Yeah?
So the first equation and second equation are in red, so they are warning about unknown variables, while the third one is in black. That's because x, y already in
Yeah. If you
Right, exactly. That's a very good observation. By the time you come to the third one, x and y are already defined, right? But here, r is not defined until you come to this part, right?
if you move the third line to the first line, you're gonna have x and y for the.
That's a good idea, right? You can try that. Because that way you will have x and y defined, and the third equation will define r. Right? But as I said, the order shouldn't matter. It should give you the same result. Okay? So this is just a warning. If it is red, it's an error, and it won't solve it. Okay? But it is an orange color. It means it's a warning to you that see something not right.
So we should ignore those.
You can try to ignore it and see whether it'll work. Yeah.
Can we define more than one variable in the same line?
We have. Right?
X comma r in the first line itself.
In the left side.
Oh,
In the left.
I don't know that.
Can we
I don't know. I'm ready to try it. Now it's red. It doesn't like that. Right?
What about
It should be the same. It should be the same. If it is, yeah. But you know, you saw the red, right? You know that if it is red, that means it's an atom. So this is a 1. Okay? So you have formulated the problem. This is a tedious way to do it. Imagine if I had 1,000 equations. I'm not going to enter like this, right? But it has an icon here for, what is this? Floppy disk icon. It says save something, right? So you can save this and see in what format it has stored it. And maybe you can write in that format and then import that, okay? Because you have an open folder too, right? So in principle, you can save these equations into a disk, or you can directly put them into the format that it expects, into a file, and then read that, okay? In fact, that's how I discovered what format it uses. It's not a very sophisticated format. Which one is that? Recycle text, yeah. So this is how it wrote. When I say save that after I define the problem, the first column is x, y, or r, and then within quotation marks, it puts the equation. So you can hide the equation within quotation marks. It treats it as a string when it reads, right? And then the next columns are initial condition and then a label, equation 1, equation 2, that I put there, okay?
I have one more question.
Yeah.
The matrix before this in the note, it was 4 by 3. 3 by
Yeah,
4.
3 by 3 or 5 by 4.
5 by 4, yeah.
Yeah.
So, what if we have more equations than unknown? So we just leave the name blank in console?
I think COMSOL might complain that it is not a well-posed problem because it doesn't have a very large linear algebra suite of tests for testing the rank. If you built this 5 by 4 matrix and then asked for a rank in MATLAB, it will tell you if the rank is 4. But you can still use the backslash operator and try to find a solution to this in MATLAB. What it will do is it will try to find the solution in the least square sense using this idea of a generalized universe. Okay. The theory of linear algebra is very well developed for problems that are non-square. Right? So you can, those are all built into MATLAB, but I don't think COMSOL knows about it. COMSOL has an iterative method for solving a set of algebraic equations. you will see later on, every differential equation is also eventually converted into an algebraic equation. At the core, it's an algebraic equation that enables us to solve it. And you'll see process of converting that. And so COMSOL has just an iterative method for solving. But you are asking good questions, and I would encourage you to try it out. Okay, that's how I learn. Okay, so what I do is if I have curiosity, you say, "Is this going to work?" And if you find something interesting, share with the class as well. Okay, so we have assembled the problem, three equations and 3 unknowns. The question is then, how do I solve? Can you take a guess? From the things that I have assembled here, I have come down all the way. I didn't have any definitions. I have put the equation. Okay, I filled that folder. That folder has this information, including the initial guess, and the description is where you can type any text. You can say equation 1, equation 2, whatever you want, right? Then there is a folder. These are the major folders, right? There is a folder called study. Okay, and that. Inside that, there's a subfolder called step 1 of the problem that I want to solve is stationary. Stationary means steady. There's no time variation in there. Okay. So if I right click on the study, you will see compute equal to sign. That means solve the problem. Okay. That's all you need to do. Once you have defined the problem, you just solve the study. It immediately creates results folder and puts the results into the results folder. Until then, this was not populated. But now it is populated. So in addition, you see here messages, progress, and log. Okay, and if you have a large problem, it will actually give you progress on the solution method. But right now, it has done it so fast, you can just look at the log. Okay, so if you click on the log folder in the output section, you will see that it actually solved it with one iteration because it's a linear problem, and it tells you what the error is. Linear error is 10 to the minus 14. So it's about 14 significant digits accurate, the result that you produced. Okay? And it also gives you global evaluate. Okay? So if you go and select from evaluate what the solution looks like, you want to see the solution, right? So you just say create a new table. And there you have the solution for the 3 values, x, y, and z. Okay? This is x. In some cases, when you're having a differential equation, the results folder will contain enormous amount of data. Then you start plotting it to look at the data. But in this case, just a table of data, just 3 values, right? So you can just see in there. Any questions on that? So it shows you how the COMSOL is structured, but I would not recommend that you use COMSOL for solving linear system equations. MATLAB is a much better tool to do that. But when you solve a system of nonlinear algebraic equations, COMSOL has some very elegant tools that are not available in MATLAB. Okay? Is the pace fine? Are you guys okay with COMSOL? Okay. Now, let's go back to the lecture and look at the next problem. This is a problem of a nonlinear algebraic equation. Okay, and this again, my apologies for non-chemical engineers. These are all coming from chemical engineering example. Okay, chemical engineers, do you recognize what that is? It's a multi-component flash column. Okay, so you have a feed. Okay, with a certain composition and components in there, methane, ethane, propane, if it's coming from a natural gas stream, or crude oil, thousands of components in there, and its temperature and pressure. In a flash drum, what you do is you flash it into a vertical drum. That means you're going to control its temperature and pressure inside the vessel, which is different from TF and PF. Aspen and HYSYS have a module. You just pull the icon for flash drum, attach one inlet stream, 2 outlet streams, define all these variables, and then you can ask it to calculate what is V. That is, what fraction of the feed goes into the vapor and what fraction goes into the liquid. And that fraction is defined as psi is equal to V over F. Okay? F is the feed rate, V is the vapor rate, and you can also calculate what the vapor compositions are and what the liquid compositions are. Again, we are not chemical engineering. This is not a chemical engineering course. I don't care how we derive this equation. We derive this equation by writing a mass balance over the entire loop for every one of the components. Okay? And we have equilibrium relationship which says that yi equals ki xi. And k is called the equilibrium ratio that comes from thermodynamics. I don't care where it comes from because I know that all I need in this course is an equation for k. K typically turns out to be a function of temperature and pressure. And those are the temperatures and pressures that I control. Okay? So by lowering the temperature, I can make more of them condense. Right? That means y will be smaller than x. So the k will be smaller. I can change the magnitude of k to change the relationship between y and x. Y is the composition of the vapor that is in equilibrium with the composition of the liquid phase. But after going through all this gymnastics, I get a single equation. This is called the Rice-Rashford equation. In this equation, the k is known and the z is known. Z is the feed composition, I told you, right? So Zi or the feed composition, if I have 10 components, I have 10 numbers for that. I know that. And similarly, ki, 1 to n, or known. What is the unknown? The unknown is psi. So I have a single equation. The equation that you see here. Okay, a single equation with psi as the unknown in that. Okay, but is it linear or non-linear? What's the definition of a linear equation? The unknown must be multiplied by a constant term, right? If you have psi square, or if you have 1 over psi, all these are non-linear terms. Here you have essentially psi appearing in the denominator, right? But remember, you need to expand this. If I have 4 components, there are 4 terms like this. But K1, Z1, K2, Z2 will all be known. The only unknown in that every one of those 4 terms will be psi. Okay? How do I solve this? Elimination doesn't work. For nonlinear problems, there is no general recipe to solve for the unknown. This is why you need an iterative method. So you make a guess for psi, put it into that, and see whether the entire function is 0. If not, devise a scheme to come up with a better psi, better guess for psi, and iterate that process. In MATLAB, there is a function called fsolve that does that. So we need to know how to pose this particular problem to fsolve so that MATLAB can solve this particular problem. But in COMSOL, you just need to enter that function in the same slot that we saw. So whether it's linear or nonlinear, it's the same idea. The function is going to be complicated, but you can type it out. Okay, and COMSOL will solve the same problem the same way. Okay. Any questions on this? So this is an example of a nonlinear problem, and let's use that to learn how to solve this. Which one do you want to see first, COMSOL or MATLAB? COMSOL is going to be pretty painful because I picked an example with 4 components. Okay, so there are going to be 4 terms. I need to type 4 of those terms into that box, but I think I've kind of pre-typed it, so maybe I can open that up. Remember, I figured out how COMSOL can read. They have it? Yeah, there. I don't know whether I can blow this up. I guess not. It doesn't give me the ability to blow this up. I don't know whether you can see in the back, but it is exactly the same format that I saw how COMSOL saved the linear set of equations. Okay? So I wrote it in a text file, psi as my unknown, and then 1 minus 3 times 0.25 divided by 3 minus 1 times psi plus 1. That's for the first component. So what is my k? K1? 3. Okay? And my Z1 is 0.25. So you need to kind of look at both of them at the same time to map the equations to this. Okay, so this is the equation that we want to enter into COMSOL box. Okay, and the way that we do that is the first three simply says what is the variable that is unknown, and then in the next box, even though I could have calculated as 1 minus 3 as minus 2, but I wanted to keep the same template. So it is 1 minus k1 times z1. Okay, so that is 1 minus 3 times 0.25 divided by k1 minus 1. That is 3 minus 1 times psi plus 1. Okay, and that ends the first term. And then the second term is 1 minus 1. I just left it as 1 minus 1, even though it is 0, because I'm saying k1 is 1. And for the third component, k1 is 0.5, and the fourth component it is 0.1. But the compositions for all the mixtures are the same. It's an equimolar mixture of, say, methane, ethane, propane, butane. So 0.25 mole fractions for each one of them. Does that make sense? How I have entered it. You can choose to enter it into the COMSOL box directly. Let me. Oh, I don't have to. I'm going to try something new in front of you. It might blow up in my face. Instead of rebuilding, okay, I can close this and I can start for a nonlinear problem and rebuild the whole thing. But it's the same set, right? So the question is, can I update these things, right? So if I say, as I said, I'm trying it fresh in front of you, so it may not work. So here is my Flash COMSOL program. I say open that. Okay. So do you see what it did?
Yeah, added one
It
more.
added one more. Okay, I was hoping that it would replace the old one and erase it, but it added one more. Okay, psi is unknown. These are the equations. It's actually dot dot says there are a lot more things. But if you place the cursor on that, you will see the full equation displayed here. Okay. So this is where the full equation is displayed for you, right? So what I need to do now is somehow delete each one of them. Right click, delete. Right click, oops. Right click, delete. And right click, delete. Okay. Now hopefully I have a well-posed problem. It's a nonlinear equation, the same way as entered the linear equation, but one equation with one unknown, and that is the equation. Okay. So it's still a stationary problem, but I have these results that were generated from the previous one. I don't know whether it's going to overwrite them or replace them with the new value, but let me just try this. Compute. That's interesting. So it am I hearing somebody from here or outside? Outside. Okay. So it kept the old one, right? So I need to delete these, I guess. Okay. Now let me try, and I need to delete the table also. So the reason I'm kind of going through this in front of you is to kind of learn that you can explore these things. So these are on each folder, and you can create folders, you can delete folders as you change the problem specification. So we really didn't restart, but we are just taking the same framework and trying to solve for the next one. So I said compute. So automatically creates a new global folder because it didn't have. Now this time it has component.psi. Okay. Now where is the result stored? That should be in the evaluate. So you create a table and it tells you what the psi value is. 0.1387. That says 13.87% of the feed is going into the vapor phase, because that's the interpretation. Fraction of feed that goes as vapor. We were at this point of 0.88. Now, the advantage with COMSOL is, if you have a problem like this, and then you say, okay, I want to make these k values that were constants in this particular case, like 3, 1.5, 1, or something like that, but they're actually functions of temperature. But I have that expression. We can go in there and define those expressions. K as a function of temperature. You can then make temperature as one of the unknowns. And you can say, now I want to achieve 50% of the feed to go to the vapor. So I give you psi, but you solve for t. Okay, so what it has to do is guess at t, get all the k values, put them into this expression, right? And then solve and see whether the function is 0. So instead of guessing on psi and iterating it, it guesses on t. But every time it guesses at t, it just goes and find the k values because I have given it the expression of how k changes with time. Right? Now I can do the same thing with pressure. K is a function of pressure. K is actually a function of both temperature and pressure. Aspen and ICES have built all these thermodynamic models for predicting K as a function of temperature and pressure. But here we need to import those functions into COMSOL in this folder, the global definitions folder. Okay? Then you can pose much more complicated problems. You can do the same thing in MATLAB too, but it requires more programming. Okay? It requires more structuring of the programs. Am I making sense? We feel that you're learning something, right? It's not overloading, right? All right, okay. You will know that when you do the assignment, whether it's overloading or not. But it has some other powerful functions that we will see later on called continuation methods, where you're trying to change one parameter and solve the problem repeatedly. And that's a powerful concept that has been implemented in COMSOL in a beautiful manner, whether it's algebraic equation or differential equation, ordinary or partial differential equation. You can solve the problem repeatedly for a whole range of parameters. Okay, so that's all I wanted to talk about COMSOL today for algebraic equations. Next class we'll come back and look at CSTR model for two nonlinear differential equations, subset of which is an algebraic equation, a steady state. But let's, we have another 5 minutes. Maybe let me try to complete this in MATLAB and show you how I would know. I think MATLAB requires more time. Flash. Okay, so this is a function that I wrote in MATLAB, and maybe I'll open it in MATLAB so that I can blow it up. We'll continue with this in the next class, but let me just set up the problem for you today. Okay, so I wrote two functions. One function that actually solves the problem by making a call to the solver in MATLAB. So for any system of nonlinear algebraic equations, the powerful tool in MATLAB is called fsolve, function solve. Okay? But you have to tell this fsolve. We will see in the later part of the course how fsolve works, what is the algorithm that we use. But for now, all I need to do is how to formulate the problem, right? So I need to tell fsolve, solve me this particular problem for the flash. So that I specify by writing my own function called flash. And remember, a function is just a rule, okay? And this rule essentially says, if you give me, and this is essentially a one-line function, because that's how it was in the typed equation also, right? It is 1 minus k times z divided by k minus 1 sine plus 1. But k can be a vector. This is where the elegance of MATLAB comes in. In COMSOL, we have to type every one of those terms repeatedly. But here, k is a vector. I can define k as a vector. I can define z as a vector. And are you familiar with the dot star product in MATLAB? It essentially multiplies corresponding elements from the two vectors. Okay? Element by element multiplication if you have a dot star. If you have a star, then it's an inner product multiplication. So MATLAB came out of linear algebra. It's called matrix laboratory, right? So it programs, the syntax handles vector matrix multiplications in a very elegant manner. But this equation is exactly the equation, the rule to calculate that function f if you give me the value of k, z, and psi. Here, k and z are constant. The psi is a guess, right? So you're telling fsolve, psi is the guess. So try repeated guesses on psi, but keep k and n as constant. Okay? Solve for psi by calling this function. So fsolve then sends out values. Psi is 0. Tell me what the function value is. So it will return the function value. It will go to fsolve. Fsolve looks at it and says it's not 0. Okay, I'll give it 0.1. Give me the value. And it says, in the first case it was 0.1. The second case it is minus 0.1. Then fsolve says, oh, you have changed sign. That means you're going through 0. Somewhere between the two guesses I gave you, 0 and 1. So it tries to bracket it to see exactly where the function is 0. So there is a lot of iterative dialogue between fsolve and flash. So, but this is the function that you write. If I give you a different problem with two equations and two unknowns, you would code them as two lines. First equation, second equation. And you will pack the two unknowns in this vector. You can have any number of parameters. So this is your problem definition in MATLAB. The problem definition in COMSOL was just typing the equation out. Here you put it into a function, and you call this function indirectly from fsolve. Okay? But by the time you come there, and I will show you next class how this is run, and I will show you some features of debugging as well. But there is a main function. I call it returns psi, and I call it just flash k. And I define the values of k, define the values of z. And here I'm giving you psi going from 0 to 1, the steps of 0.1. The reason I want to do this is I want to first plot that function to see how the function looks. Where does it cross the root? Then I know approximately where the root is. Because it's a one function in one variable, I can do that. So I create a vector of psi and calculate the function values by putting it through the loop and plot that function. Once I know where the root is, then I make a call to fsolve to get the actual solution. Okay? So we will go through this step starting in the next class, and then we'll move on to more complicated model building, but one in each class. Okay, linear, nonlinear, and then ODE, initial value problem, ODE, boundary value problem, and then some PDEs. Then we will move on to continuum mechanics, developing the Navier-Stokes equation, averaging concepts, etc. Okay, so I think maybe that's a good place to stop. Any questions? All right, so see you on Wednesday.